This ramp on a sort of earth dam on a levee, it goes up approximately, it goes up more than 40 feet to cross this railway here and highway, and you see it gently slopes down with about 3% on a earth dam, and we could do this for the road over a greater length and creating that amphitheater in the green grass. So, and here you see some stairs integrated for the also for the pedestrians that want the shortcuts, I would say. But yeah, I have to think about it. This bridge is a project which is already built, and we use the same concept then for the for a bridge over the highway, where we first were asked to widen an existing viaduct to create more traffic lanes and also being able to keep in place the existing bike path. But for this project, we came to the conclusion, and that's why network analysis also as a designer is very important. We came to the conclusion, well, widening this viaduct will cause a lot of hindrance for existing traffic on this big highway in the Netherlands. And for this highway, you have to sort of imagine, this is all the sort of highway, you have to imagine that all the goods that come into the port of Rotterdam, the biggest port of Europe, are transported over the road into Europe over this highway. So it's a major highway and very important. And we only could close this highway one night in a weekend in a holiday season. So we had to come up with a good smart solution. And at first the client wanted us to widen the existing viaduct, but we came to the conclusion that widening an existing concrete viaduct with new girders, etc., would cause much more hindrance for the existing traffic on the highway and all the truck traffic. So we researched this, and let's see what the image is. We researched it as this and came to the conclusion that actually it would be better to make a one large span bridge a little bit south of the existing viaduct, because it would be better connected to the existing utilitarian and recreational bike network, but also because you could build this bridge could also span the off ramps and the on ramps on the highway, so the cyclist wouldn't need to use the traffic lights on the start of the on ramp and the end of the off ramp anymore. So it was better for car traffic flow. And we do most projects of us for biking are to improve car traffic flow, and we researched for this bridge a lot of the bridge types: an arch bridge, a Warren truss bridge, a cable stayed bridge. And this is then an example of an arch bridge we researched, and this is a bridge which is already built now, and it is over a canal. And in Dutch canals, well, you have to go up at least 10 meters, so at least 30 feet above the canal, because the canals are used with barges with double layers, containers, etc. And this bridge also had to go down on the other side of a levee a couple of meters, so say 10 feet down, so the total feet height difference to overcome is in the direction of 40 feet. And this bridge has a main span of 104, so more 320 feet, and ramp lengths of more than 1,000 feet on both sides. And like you can see here, these are some figures, but like you can see this very optimal arch main span in the Netherlands, you can build this for 1.5 million euros, so $1.5 million. And the total cost of this project of a very comfortable bike bridge going up 13 meters, spanning 104 meters, so 8.2 million euros. And we use this concept as one of the concepts for the bridge over the highway in Eindhoven also, but other concepts we researched were a modular truss bridge like this design we proposed for Singapore, with a top deck for pedestrians and a bottom deck for cyclists, because you can fill the truss with green and you create more comfort in a hot climate like Singapore. This is a cross section of that truss bridge. And we also researched cable stayed bridges like this bridge for over another highway in the Netherlands. But we came to the conclusion in the end that actually an optimized arch bridge it's a netted arch bridge, netted cable stayed arch bridge was the most optimal solution, because we could only close this highway for one night in the weekend in a holiday season, because it's a major highway which is used to transport all the goods from the seaport Rotterdam into Europe. And it was not possible to build piers inside this highway It could be done, but would have caused a lot of hindrance for car traffic and freight traffic. So it was not preferred by the Dutch DOT, so to say. And also, not needing any piers, you have longer sightlines as car traffic. So you have a much safer situation for car traffic because you can just look under an arch bridge. And this arch bridge was built next to the highway here, and it will be just wheeled in or rolled in one night. And here you see some other views of the arch bridge, impressions of the how it will look, and you see it's good to see here that it's a netted arch, and a netted arch is a little bit more complicated to tension while building, but in the end you need a lot less steel with a netted arch than the more standard arch with vertical cables or vertical rods, so to say. And it's easy to light it. And Eindhoven wants, like Boston, wants to be a really high-tech city, so they want to light their infrastructure, showing off how good they are in optimizing infrastructure. And this is also on both sides of this bridge are new high-tech residential business areas planned, and Tesla's going to the right side, I think, and Google on the left side, and some cafeterias, etc. So this should be Boston, actually. And well, this was the project we used, which we already has been built, which was a sort of example or a reference project for the arch. And here you see that the main span of this arch. Here you see, the main span only cost 1.5 million euros by optimizing it.
Was that a netted arch as well?
This is also a netted arch, yeah. And contractors in the Netherlands sort of discussed this with us, that a netted arch is harder to build, etc. And but in the end, it saves a lot of money for the client.
Was it rolled into place or lifted by crane?
This one was. This is over a canal, so this was floated in by a barge with hydraulic supports.
Okay.
And the rest was already made, the ramps, and then it was just lifted up a little and placed on its supports, let down on its supports.
How about the other one over the 14 lanes? That one.
This one will be wheeled in by those big vehicles with a lot of wheels, which can be remotely driven, and will a part of the guardrails will be taken away for a little while, and it will be just wheeled in one day.
And hydraulically lifted as well?
Exactly the same way, hydraulically lifted and put on place.
2 questions, if I could. A netted arch bridge, are there examples in the United States of such structures?
I have to look that up. I don't know for sure. I know actually for sure because a colleague told me that I think the United States Army Corps or the United States Marine Corps built a temporarily and now, not temporarily, but forever there, bridge like this, road bridge, somewhere in the Middle East as a reconstruction thing. I don't know exactly where, Iraq or... So there are a lot of engineers in the USA having experience with it, and they built a road bridge like this. And the ramp for this bridge is about 1,000 feet long, and it has very comfortable curves, so people cycling down or even on mopeds can use it with high speeds up to say 20 miles an hour at least. And the width of the ramp is about 15 feet, so it can be also comfortably used.
Is that 15 feet widened in the curves?
Yeah, it's more than 15. No, it's on the straight parts. It's 15 feet wide, or a little bit more, 18 feet or so. And in the curves, we made it a little bit wider even to create more comfort and safety. And this structure is cast on site in place. Usually, we work a lot with prefab.
Segmental
prefab, that's modular, only needing one mold, and in that way create economies of scale and save a lot of money.
And then sort of tension together, some sort of post-tensioning
depends.
To connect the segments?
It's not always necessary. It depends on if, say, a department like maintenance is okay with having expansion joints or not.
Okay.
When expansion joints, standard rubber expansion joints are okay. You can do just segments that are completely prefabricated and then put in place and put the expansion joints between. And sometimes when you want to have larger spans, say up to 90 feet or so, it can be more efficient to make a more integral structure, which is melted together by pouring concrete and continuing the reinforcement, and then you don't need expansion joints, and it's not segmented anymore, of course. But also that we do this with prefabbing segments, which act as a formwork that stays in place. So a concrete formwork which is then filled up with concrete to make an integral bridge.
Could you talk a little bit about this project, and if you think that how you feel about the heights and the spans, and
no, of course,
how challenging or doable that would be?
Can I ask one preliminary question? Yeah. In both examples of the netted cable arch bridge, is the I don't know the correct term. Is the deck the horizontal span?
Yeah.
Is it flat, or is it also have a small arch to it?
It has a very, very small arch to it. It's I don't know this for this thing, but you never sort of build straight bridges because optimally they seem to sink a little, and also for water collection. So like here we have a lot of snow and water, so we also always give it a little bit of an arch.
Okay.
The deck to get the water off.
Okay.
With regard to the throat area, there's for the project this ramp, it goes up about 50 feet. So when you compare it to the vertical clearance needed above a road, I saw here minimal 11 feet. Well, it's very minimal. I think it should be in the Netherlands. It should be more. In the Netherlands, we need at least about 15, 16 feet.
Yes.
So and for this a ramp like this would be easily enough to overcome a sort of double layered road structure like which is proposed in the throat area.
And so what's the clearance where that road crosses over the bridge?
Where that bridge crosses over the road, it's much more than required in the Netherlands because the vertical clearance needed over the water is much higher. So it could go much lower.
Water?
No, that's road.
Okay.
But here when it goes over the water, the clearance needs to be 30 feet plus. So it's higher above the road than it needs to be. It could be much lower above the road because the vertical clearance above the water, required vertical clearance is much higher because of the large cargo ship. So a car vertical clearance in the Netherlands is about 14, 15 feet.
Mm-hmm.
But the vertical clearance required above the water, that was about 40 feet. So it's cargo ships in the Netherlands is very important, and they sort of determine the height of the structure, and this is a big vertical height difference of about 50 feet, and it's you could easily overcome a double layered road with a ramp like this in a comfortable way. I could show later a video. And here you see the arch bridge during construction, and for structures like this we also build an arch bridge. The arch bridge we're now going to build over the 14-lane highway has a length of 500 feet.
This length of this arch bridge that we're seeing in this photo is
this length is about 125 feet. It's bigger. It's 105 meters, so it's about 315 feet and a little bit more, so 325 feet.
Wow. Okay.
The thing is with this bridge, we're now building the other one over the highway, and it's 130 meters, so it's about say 420 feet, and this is really an engineering thing. By building an arch in this way, you only need 270 tons of steel. So empowerment, and when an engineer sees this, that's not that much. It's really optimized, and we use programs to optimize. We use Grasshopper and Rhino to optimize it. I can show a picture of that also. Here you see a cross section of the bridge. You see it's 5 meters width, so that's about 18 feet width, and that's enough for a 2-lane bi-directional bike path for really heavy use, and also enough to allow some pedestrians on it. And you see that the structure of the arch, the deck structure consists of two edge girders made from steel, and in between the edge girders we made a concrete deck, and the concrete deck here makes really sense. Like here in Boston in the United States, I see a lot of concrete decks. I think, well, this could also be a more lightweight deck. It's not necessary. We wouldn't do it, but for this bridge we did it, this type of bridge, because the concrete creates extra weight and thereby stability for the netted structure of the arch. And here you see the bridge during construction. So you see that first the steel structure is made, and there are some